You know, when you look at a really massive, sprawling city skyline, you rarely actually think about the plumbing.
Right. No, you definitely don't.
I mean, you don't stand at the base of a 100-story skyscraper and look up at the clouds and marvel at, like, the HVAC system or the load-bearing distribution algorithms.
No, you look at the glass, you look at the height, you notice the aesthetics and the way the light reflects off the facade at sunset. Because the human brain is just wired to appreciate the surface layer, the completed vision.
Exactly. We just see the shiny exterior. But underneath all of that visible beauty, there are miles and miles of standardized pipes and specific voltage grids routed with mathematical precision and really strict zoning laws.
Right, the hidden stuff.
Yeah, because without those hidden, highly regulated systems, the entire city just collapses. The absolute second. 1 million people try to flush a toilet or turn on a light switch at the exact same time. The scale destroys the structure if the infrastructure isn't rigid.
It is the invisible infrastructure that makes the visible beauty functional. I mean, it's the standardization, the rules of the road, basically, that prevent absolute catastrophic gridlock.
And that dynamic is exactly what it feels like when you first step into the world of digital product creation at an enterprise scale.
Oh, totally.
If you are just starting your career as a designer or a developer or a product manager, you might look at a massive application and think, it's all about the shiny facade. You see the slick animations and the intuitive flows and the beautiful typography.
Right, you just see the UI.
Exactly. But today, we are going completely under the hood. We are going to demystify how massive tech teams actually stay organized, and we are giving you a shortcut to understanding the invisible digital infrastructure that holds the modern web together. So welcome to today's deep dive.
And this is genuinely one of the most critical topics for anyone who really wants to understand how scale actually operates in the tech industry. Because understanding design systems isn't just about knowing what color a button should be. It is like being handed the structural blueprints of that skyscraper before you even learn how to pour the concrete. It dictates the entire workflow.
It creates the language, right?
Exactly. It creates the language that allows cross-functional teams to communicate without completely destroying each other's work.
And to give you that exact blueprint, we're focusing heavily today on Chapter 26, Design Systems. This is coming straight from an incredible field manual for this stuff, a book called Design User Interface.
A phenomenal resource.
It really is. And our mission today is to break down these core design concepts from Chapter 26 so you can walk into any product team, sit down at the table, and immediately speak their language.
The frameworks outlined in this chapter are foundational. They bridge that enormous gap between the abstract artistic process of like making something look beautiful and the harsh concrete reality of making something deployable and maintainable across a globally distributed engineering team.
Absolutely. But before we really get into the weeds of the architecture, I want to make sure you have this material in your own hands. You can find the exact source we are tearing down today by going to the book link, which is https://hypeforacademy.gumroad.com/Lou-book.
Though honestly, you don't even need to type that out.
Right? No, don't type it out. Just open your phone and scan the QR code of the book link that we have provided in the description below. Grab the book and follow along with us.
Highly recommend having it open.
Yeah. And while you're looking at the description, we explicitly request that you hit follow on the show. We are constantly breaking down these highly technical design frameworks and bringing you the career-building content you need to navigate this industry.
Because it's the kind of reference material that pays dividends over an entire career. I mean, as we are about to explore, a design system is emphatically not just a shared Dropbox folder full of logo PNGs and a PDF of hex codes.
Right. It's so much more than that.
Yeah.
And Chapter 26 establishes a really critical baseline, which is that a design system is the active living intersection of design code and product future-proofing.
So let's start at ground zero. Why do we even build these systems? Like, what is the actual architectural failure that occurs if we just let teams wing it?
We really have to experience the chaos to appreciate the system.
Fair point.
A design system fundamentally is a collection of methods and processes that force a kind of collaborative sanity on digital product teams. In practical engineering terms, it functions as a documented version-controlled library of code-ready components. But why the reason companies invest millions of dollars into building these comes down to the brutal reality of scale.
Scale. It's the metric every single startup is chasing, but it's the exact thing that routinely breaks their internal culture and their product quality.
Precisely. Let's look at the life cycle of a typical digital product. It almost always begins as a hyper-tight collaboration. You have one designer and one front-end developer.
The dream team.
Right, the classic duo. And at that stage, communication is basically telepathic. The designer mocks something up, they hand over the Figma file, and the developer implements it.
If there's a slight discrepancy in how a drop-down menu should render, the developer just rolls their chair across the room, points at the screen and asks. They share a single mental model of the product.
They are essentially a single operational unit. There's zero friction in the feedback loop.
But then the product finds product market fit and the company scales.
And then everything breaks.
Exactly. Suddenly you don't have one designer and one dev. You have 5 agile squads. Then you have 20 designers and 50 developers. They're scattered across 3 different time zones. They are working on entirely different features of the same application simultaneously. And this is where the divergence of truth begins.
Because you just can't roll your chair over anymore.
No, you can't.
You are relying on project management software Jira tickets, formal sprint planning meetings. And the reality is, human beings hate friction. If a developer in Berlin needs a quick clarification on a padding value from a designer in San Francisco, they aren't going to wait 12 hours for a formal Jira response.
Exactly. So decisions start happening entirely outside the official documented channels.
Right.
They happen during lunch breaks. They happen in transient, undocumented Slack direct messages. They happen during a 30-second chat in the elevator. A designer makes a localized decision to round the corners of a specific modal window just a bit more because it feels right for their specific feature.
I look at this almost like forking a code base. But you are forking the collective human memory of the company.
Oh, that's a brilliant way to frame it.
Because every time a localized decision is made without updating a central repository of truth, a new mental fork is created. The team working on the checkout flow thinks the brand uses an 8-pixel border radius on absolutely everything. But the team working on the user profile section thinks it's a 4-pixel radius because someone casually mentioned it in a Slack thread like 3 weeks ago.
And the inevitable result of these mental forks is massive technical and visual debt. The chapter actually highlights a fantastic real-world manifestation of this.
Oh, the login form example.
Yes. They analyzed a huge, globally recognized brand application. And within the exact same app, the login form and the registration form possessed entirely different UI architectures.
I know exactly what you're talking about. You see this all the time with legacy applications that are trying to modernize. You click sign in, and you are presented with a gorgeous modern React interface built in 2024. Floating labels, smooth focus states on the inputs. Perfect micro interactions.
It looks great.
It looks beautiful. But then you realize you don't actually have an account, so you click register. And the URL routes you to a different subdomain, and suddenly you are looking at a brutalist web portal from 2012.
Oh yeah, the shock is real.
The text inputs are completely different. The primary CTA button is a totally different shade of blue. The typography scale is completely shattered.
And from a systems engineering perspective, we know exactly why that happened. The login team was probably an entirely different agile squad than the identity and access management team who owns the registration flow. They were working in silos, but to the end user, your internal org chart is totally irrelevant. When the user experiences that disjointed transition, it actively shatters their trust. It causes massive cognitive friction.
It makes the software feel really cheap. It reminds the user that they are using a machine built by fragmented teams rather than experiencing a cohesive digital environment. Honestly, when the inputs change shape like that, a subset of users will legitimately wonder if they've been victimized by a phishing redirect.
That psychological impact is real. Users rely on internal consistency to navigate complex applications. When you break that consistency, you actively increase their cognitive load.
You have to relearn it.
Exactly. They have to relearn how to interact with your software on every single new page. But beyond the user experience, there's a massive business cost here too. Without a system, highly paid engineers and designers spend hours arguing in PR reviews about what shade of gray a disable button should be. It is an extraordinary waste of resources.
So the goal is to eliminate the localized arguments. We need to build an architecture that makes the right design decisions automatic, freeing up the team's mental bandwidth to actually solve complex business logic rather than constantly debating hex codes.
Precisely.
But if I'm a developer or a designer staring at a sprawling, chaotic application right now, how do I actually build this central source of truth without grinding all product development to a complete halt? Like, how do you systematize a million moving parts.
Well, you don't start with the sprawling application, you have to go microscopic.
Okay.
The framework we are exploring introduces a foundational concept for organizing this chaos, and it's called the tree-like structure. This is heavily adapted from Brad Frost's methodology of atomic design, and it fundamentally changes how you perceive user interfaces. You stop looking at pages and you start looking at molecules.
I really want to dig deep into this because atomic design is one of those buzzwords that gets thrown around in stand-ups constantly. But the actual mechanical implementation is often deeply misunderstood.
Oh, absolutely. People use the terms without understanding the physics.
Right. The progression moves from atoms to molecules to organisms to templates and finally to pages. Let's break down the actual physics of this. In a modern reactor view environment, what is an atom?
An atom is the absolute indivisible base value of your UI universe. It is a primitive. We are talking about the raw data points that cannot be broken down any further without losing their fundamental properties.
Like a color.
Exactly. A single color hex code is an atom. A specific font weight is an atom. A Bezier curve value for an animation timing function is an atom.
Okay.
Crucially, an atom on its own doesn't render anything useful for the user. It is purely a stylistic variable.
Right, because if you just hand a user a hex code, they can't click it. There's no utility. But in modern front-end architecture, we combine these conceptual atoms into molecules.
Exactly. A molecule is the smallest functional group of atoms. Think of an HTML label element paired with an input field wrapped in a specific margin atom. It now has functional purpose, the user can type into it, but it's still relatively simple.
And then we scale up to organisms. And this is where I think the cognitive shift really happens for teams adopting this.
It's the biggest hurdle.
Because the book deconstructs a primary submit button, framing it not as a basic HTML element, but as a complex organism. Which on the surface sounds like massive over-engineering. I mean, it's just a button, right?
It is never just a button.
Yeah.
If you treat a button as a single monolithic asset, your system will fail. The architectural philosophy here is radical deconstruction. A button is an organism constructed from highly specific atomic properties.
Okay, so break that down. What's in the button?
Well, it has a geometric shape, say a rectangle with an 8-pixel border radius atom. It has a background color atom. It has typographic atoms like font family weight line height.
Yeah.
It has spatial atoms like the exact mathematical padding between the text node and the bounding box.
And it has interaction states too, right? The hover state, the active state, the disabled state. Each of those requires a different combination of atoms. But let's look at a specific example of isolating a variable here, because the chapter points out a very specific method for handling things like drop shadows.
Yes, the shadow isolation is a perfect example of scalable thinking. In a naive system, a designer just applies a drop shadow to a button and calls it a day.
Like just eyeball it.
Exactly.
Yep.
But in a robust design system, that shadow must be abstracted into its own distinct documented atomic category. You might define an atom called shadow/CTA for your call to action elements.
And that shadow/CTA definition strictly dictates the X offset, the Y offset, the blur radius, the spread radius, and the RGBA color value with its exact opacity.
Precisely. You define it once. And the reason you do this is for horizontal scalability. Because tomorrow, the product owner might request a new UI element, perhaps a floating sticky banner for a promotional sale.
Right.
That banner also needs to hover above the content. Instead of the designer manually tweaking a new shadow and just guessing what looks good, they simply apply the existing shadow/CTA atom to the new banner organism.
You are injecting the exact same visual DNA into an entirely different component.
Yes.
That is how a massive application maintains structural integrity.
But I have to push back here because this level of granular atomic control terrifies a lot of creative professionals.
It does. I hear it all the time.
I mean, if I am defining the exact blur radius of a shadow as an immutable law and restricting designers to basically assembling pre-approved atomic Lego bricks, aren't we just creating a massive bureaucratic bottleneck?
It feels like that at first.
Like if a designer realizes a softer shadow would make a specific data visualization widget much more readable. Do they really have to file a JIRA ticket petition the design system committee and wait 2 sprints just to change a blur value? It feels like the death of intuitive design.
It's the most common criticism of design systems,
Right.
but it fundamentally misinterprets the goal of the architecture. A design system is a baseline. It is not a prison.
The authors of Design User Interface make a really compelling argument that this systemic restriction actually liberates creativity. Think about the cognitive load of a designer who doesn't have a system.
They're constantly guessing.
Right. They start a new feature, and they have to mentally litigate every single micro decision. Is this blue accessible against this gray? Is 16 pixels enough padding for a touch target on mobile?
They're essentially reinventing the wheel on every single screen.
Exactly. By offloading those solved problems to the design system, you eliminate the micro-decision fatigue. The designer doesn't have to worry about the mathematical soundness of the margins or the WCAG compliance of the contrast ratios. Those are solved at the atomic level.
Which frees up the brain.
Yes, this frees up massive amounts of mental bandwidth for the designer to focus on macro-level innovation. They can focus on user flows, psychological friction points, complex state management, and the actual business logic of the interface.
Okay, I see that. You are constraining the stylistic variables to elevate the functional thinking. And realistically, if a team truly needs a novel UI pattern that doesn't exist in the system, they just build it right.
Of course.
You construct a new organism, you test it, and if it proves valuable, you abstract its atoms and integrate it back into the global system. It's an extensible API, not a closed box.
Exactly. But for that extensible API to work, it needs a centralized brain. It needs a set of absolute immutable laws that govern how those atoms are allowed to behave. And that brings us to the next massive conceptual pillar, which is global rules.
This is where we bridge the gap between design theory and actual code implementation. When we talk about global rules, we are primarily talking about the foundational trinity: colors, typography, and the spatial grid.
The big three.
Yeah, these dictate the rhythm of the entire application.
And the discipline required to maintain these global rules is intense. Let's look at color strictness for a second. The chapter emphasizes a workflow rule that is very, very hard for junior designers to adapt to.
What's the rule?
Once your global color library is established, you must actively avoid using the manual color picker tool in Figma or whatever design software you use.
Oh, wow. So no color picker at all.
You never manually set an object to a random hex code. Every single color assignment must be linked directly to the global style library.
The manual color picker becomes the absolute enemy of scale. Because if you hard-code a button to a specific hex code manually, you have severed it from the central nervous system.
Precisely. Let's trace the catastrophic ripple effect of that manual override. Let's say a designer hard codes that hex value across 50 different screens.
Sounds like a nightmare waiting to happen.
It is. 6 months later, the marketing department does an accessibility audit and realizes that specific blue fails contrast ratios for visually impaired users. They need to shift the brand blue to be 10% darker.
And if the system is hard-coded, some poor junior developer has to run a massive, risky find and replace across the entire codebase.
Yeah.
Or a designer has to manually click through hundreds of design files to update that color. It takes weeks, and they will inevitably miss a few instances, creating that visual debt we talked about earlier.
But if you followed the global rules and every button was linked to a semantic variable named brand primary action, updating the application takes about 30 seconds.
It's basically instant.
Right. You change the hex code in the central global rule, and it propagates perfectly across thousands of instances instantly.
Which naturally brings us to one of the most powerful implementation mechanisms in modern UI engineering design tokens. The chapter focuses heavily on this, and I want to really unpack how tokens operate at the code level, because it completely changes how front-end developers write CSS.
Design tokens are the ultimate realization of atomic design. They are essentially overriding platform-agnostic variables defined in a single, centralized location.
Let's use the grid as an example here. The framework advocates for a soft grid concept typically based on an 8-point system.
Right, the 8-point grid.
This means every margin, padding, and layout dimension should mathematically divide by 8. So you have values of 8, 16, 24, 32, 48 pixels. Now, historically, a developer would just look at a design file, see a 16-pixel gap, and write margin bottom 16px in their CSS. Why is that considered a massive anti-pattern today?
Because 16px is a magic number. It has absolutely no semantic meaning.
Magic number.
Yeah. When a different developer looks at that code a year later, they don't know why it's 16 pixels. Is it 16 pixels because it's a structural layout gap? Is it 16 pixels because it's the specific internal padding of a card component? We don't know. It is a raw integer floating in a void of context.
And if it lacks context, it lacks scalability.
Exactly. This is where the token architecture comes in. Instead of writing 16px, you utilize a design token typically formatted as a JSON key value pair in a central repository. So you define a primitive token, like spacing 100 equals 8px, spacing 200 equals 16px.
Okay.
Then you map those primitives to semantic tokens. You might define token margin standard equals spacing 200.
Okay, let me translate the cascade logic of that for a second. In my actual component code, say I'm building a React component, using styled components, or even just modern CSS custom properties.
Yeah.
I am not writing margin 16px. I am writing margin var, token margin standard.
Yes, exactly. You have abstracted the value away from the component. The component no longer knows or cares how many pixels its margin is. It only knows that it must ask the global token file for the standard margin value.
The power of that abstraction is staggering when you think about multi-platform scaling. If you have a JSON file acting as your absolute source of truth, you can use build tools to compile that single JSON file into CSS variables for your web app, into Swift variables for your native iOS app, and into XML for your Android app.
That is the holy grail of design systems. A single source of truth dictating the physics of multiple independent software platforms.
It's incredible.
If the leadership decides the entire ecosystem needs to feel airier and less dense, you don't rewrite tens of thousands of lines of code across 3 different tech stacks. You go into the central JSON file change spacing 200 from 16 to 20, trigger a global build pipeline, and every single application scales up its breathing room mathematically and perfectly.
It is absolute God-level control over the UI. But with that kind of centralized power comes a massive risk.
Huge risk.
If changing one JSON file alters the entire suite of company applications, where does that file live? Who gets to edit it? How do we protect the source of truth from human error? This really shifts our deep dive from design architecture into raw engineering and governance. We have to talk about code as the ultimate gatekeeper.
And this is where the philosophy outlined in the chapter takes a highly controversial, but in my view, incredibly necessary stance.
Okay.
When a company decides to build a documentation wiki for their design system, the website where all these rules tokens and components are displayed for the team to reference, the immediate impulse is to use a CMS.
Right, a content management system. Something like WordPress or Notion or an internal Confluence wiki. It makes intuitive sense. You want a democratic, user-friendly platform where a product manager can easily log in, click an edit button, fix a typo in the documentation, upload a new screenshot, and click save.
It sounds agile. It sounds efficient. But the authors of the chapter argue, based on deep industry experience, that democracy in a design system's core documentation inevitably leads to rapid entropy.
Wait, I have to challenge this. Forcing all documentation into a code repository adds immense friction to the workflow.
It does.
If a UX writer wants to update the grammatical guidelines for error messages, you're telling me they shouldn't be able to just edit a text field. They have to interface with an engineer, create a branch right markup, and go through a pull request review. That sounds like a bureaucratic anti-pattern that slows everything down.
It absolutely adds friction. But in this specific context, the friction is the feature.
The friction is the feature.
Yes. It is a concept we can call controlled chaos. The fundamental argument is that the easier a system is to modify, the faster it degrades.
Okay.
If you have 20 different admins, designers, writers, managers with the power to instantly tweak the system documentation via a CMS, the system fragments. Someone adds an undocumented exception for a specific client project. Someone uploads a deprecated component. The documentation drifts away from the actual production code base.
Ah, the drift. The documentation says the button should be blue, but the production code is rendering it purple, and nobody actually knows which one is the approved standard.
Exactly. To eliminate the drift, the text takes a hardline stance. The design system documentation wiki should ideally be built natively in code, meaning the documentation is a software product.
Right.
The front-end developer becomes the absolute gatekeeper. If you want to change a rule, you don't edit a text box. You must write code, commit it to a Git repository, pass automated CI/CD checks, and deploy it.
I actually love the psychological and cultural shift this forces upon a product team. Historically, design hands a PDF over the wall to development, and development blindly builds it. But if the developer is the sole gatekeeper of the sacred text, if they literally have to code the rules into the system wiki, it forces deep integration.
It forces cross-disciplinary negotiation. The developer cannot be treated as an assembly line worker anymore. They become a highly active, integral architect.
Because they have to build it.
Because they have to physically write the React code or the CSS that defines a new component in the wiki. They are forced to ask highly specific mechanistic questions during the design phase.
They act as the ultimate logic filter.
Yes.
If a designer proposes a new animated loading spinner, the developer who has to code it into the system will look at it and say, okay, this looks beautiful in Figma. But does this animation curve map to our existing atomic tokens? Does this infinite loop respect the user's prefers, reduced motion operating system settings for accessibility? Can we render this without dropping the frame rate on a low-end Android device?
Exactly. They vet the logic before it ever becomes a rule. And regarding the underlying technology of the wiki itself, the chapter notes that React.js has become the gold standard for building these documentation sites.
And let's explain why React is uniquely suited for this, rather than just saying it's popular. It's about the architecture of React itself.
Right.
React is fundamentally built on the concept of isolated reusable components that manage their own state. It perfectly mirrors the atomic design philosophy.
It is a one-to-one translation. In Figma, you have a master component with variants. In React, you have a functional component that accepts properties to alter its render state.
Right.
If your documentation wiki is built in React, you aren't just showing a static picture of a button, you are rendering the actual living production code of the button directly on the documentation page. The documentation is the code.
That eliminates the drift completely. But I want to highlight a massive caveat the chapter throws in here because it's a brilliant piece of pragmatic engineering advice.
Not the CSS snippet rule.
Yes. Even if you build your entire ecosystem in React, the chapter stresses the absolute necessity of maintaining plain vanilla CSS or SCSS code snippets alongside the React components. Why? If React is our unified source of truth, why are we keeping decoupled CSS style sheets around?
Because enterprise architecture is messy and you have to plan for stack diversity. React is powerful, but it requires a massive JavaScript runtime environment.
Yeah.
Now imagine your marketing team needs to build a highly optimized lightweight landing page or a simple animated HTML5 banner ad.
Forcing them to load a 150 kilobyte React framework just to render a button on a banner ad is catastrophic for performance. It's basically engineering malpractice.
Exactly. But you still desperately want that banner ad to look visually identical to your core web app. It needs the same brand DNA. By ensuring your design system generates agnostic CSS snippet files, essentially compiling those design tokens we talked about into raw CSS variables, any team using any technology stack, from a legacy PHP backend to a static HTML site, can link to that style sheet and instantly inherit the global rules, the correct typography, and the atomic layouts.
It provides rigid rules with flexible implementation. And speaking of implementation, there's a vital logistical note in the chapter regarding version control. When you update these systems, they recommend abandoning semantic versioning for the documentation, like calling it version 2.4.1, and instead simply using the deployment date as the version identifier.
It is a small change that massively improves human parsability.
Makes so much sense.
Right, because when a designer is trying to figure out why a component broke knowing it changed on October 12th, gives them an immediate chronological anchor to cross-reference with other company events or product launches, whereas version 2.4.1 is an abstract sequence number that requires looking up a changelog to understand.
Okay, so we have this incredibly robust, token-driven, React-rendered, gate-kept code repository. It is mathematically perfect.
And paper.
On paper, exactly. Because here is the fatal flaw in pure engineering solutions human beings have to use it. If a brand new junior designer or a non-technical product manager opens this system to figure out how to build a user flow and all they see are React prop types and JSON token structures, they're going to freeze. The system fails if it is incomprehensible to non-engineers.
Which brings us perfectly to the critical translation layer of the system visual documentation.
Yes.
A design system wiki that only houses code is not a system, it is just a repository. The text is adamant about this requirement. The code must be contextualized visually.
How do we build that context? Like, what does good visual documentation actually look like in practice?
It relies heavily on high-fidelity visual examples, usually embedded components or screenshots placed directly alongside the code, accompanied by strict scenario-based usage guidelines.
So not just a button floating in a white void.
Exactly. You don't just render the search bar organism in a vacuum. You visually demonstrate the search bar sitting inside a global navigation header, and then you show another example of it deployed as a massive hero element on a landing page. You show the context.
And the chapter emphasizes a specific psychological approach to writing these guidelines that I think every single engineering and product team needs to hear. They call it the state, the obvious rule.
It is the ultimate weapon against tribal knowledge. When structuring documentation, you must write down the rules that seem incredibly intuitive to the senior staff. You must state the obvious.
Let me speak directly to the listener for a second. If you have ever been onboarded at a new tech company, you know the exact anxiety I'm talking about. You are handed a massive documentation wiki. You read a components page 3 times. It lists the padding, it lists the React props, it shows the hex colors.
But it misses the context.
Exactly. It doesn't tell you whether the submit button is supposed to go on the left or the right side of the modal window. You don't know because the senior designer who wrote the wiki thought, well, obviously it goes on the right. Everyone knows that.
That is the curse of knowledge. The people building the system have internalized the logic so deeply they forget that it is actually arbitrary.
Exactly. And because the obvious wasn't stated, the new hire feels stupid asking. They guess they get it wrong, and it creates friction in the pull request. Stating the obvious in documentation, literally writing the sentence, the primary CTA button is always placed flush right within a modal action bar, is the highest form of professional empathy. It removes ambiguity and accelerates onboarding.
And to achieve that level of comprehensive, empathetic documentation, the text outlines the minimum operational triad required to govern the system. You need at least 3 dedicated perspectives.
Let's break down the triad.
First, you need a UI/UX designer. Their role is to define the visual logic, ensure the typography scales perfectly, and guarantee the accessibility contrast ratios are mathematically sound.
Makes sense.
Second, you need a product owner. Their role is often overlooked, but they ensure the design system actually serves the business goals. They prioritize which components get built based on the product roadmap.
Okay.
And third, you need the front-end developer acting as the technical architect and the code gatekeeper we discussed.
And the magic really happens in the overlap between those roles. The chapter makes a profound point about cross-disciplinary fluency. It argues that the absolute best developers for a design system are the ones who possess an intuitive grasp of UI design principles.
Yes, absolutely.
They don't have to be able to design a logo, but they need to understand typographic rhythm.
Yeah.
They need to understand why an optical alignment might look better than a strict mathematical alignment.
And conversely, the most effective system designers are the ones who understand the fundamental physics of the DOM, the document object model.
Right.
A designer doesn't need to write production-grade React hooks, but they must understand how the CSS cascade works. They need to understand how Flexbox algorithms distribute space, or how position absolute removes an element from the document flow.
Because if the designer understands the limitations and behaviors of the rendering engine, they won't design an atomic structure that is a total nightmare to code. When the designer thinks in CSS and the developer feels the UX, the system thrives. They share a unified vocabulary.
Okay, so let's assess where we are right now. The system is documented, the tokens are centralized in JSON, the rules are gate-kept in a React repo, the documentation is highly visual empathetic and states the obvious. The triad is working in perfect harmony. Are we finished? Is the system complete?
In software engineering, the word complete is a very dangerous illusion. If you lock the system and walk away, it immediately begins to decay as user needs evolve. So we have to look at the final and arguably most dynamic concept from Chapter 26, which is research and development. A design system is a living organism that must respond to environmental stimuli.
The authors explicitly state that a design system is never truly done. It must be treated as a product itself, subject to continuous iteration. New accessibility research shifting industry interaction paradigms and raw user analytics must drive global changes. And the chapter provides a highly mechanical example of how data forces a system to evolve. The radio button interaction analysis.
Oh, I love this example because it bridges the gap between abstract design theory and harsh empirical user data. Walk us through the mechanics of this scenario, because this is how elite product teams actually make decisions.
Okay, so imagine your design system has a standardized radio button component. It's mathematically perfect according to your grid. It's been deployed across the application for a year. But your analytics team comes to you with a heat map and an interaction analysis.
Okay.
The empirical data shows that a statistically significant number of user clicks are falling just outside the active area of the radio button.
Let's translate that. In UI engineering, we talk about the hit area, or the interactive bounding box of an element. Users are physically trying to select the option, but their mouse cursor or their finger on a touchscreen is missing the mathematically defined hit area by just a few pixels.
Yeah.
Nothing happens. They experience rage clicks, they have to readjust and click again. It completely breaks their flow state.
It is a massive usability failure, often governed by Fitts' law. That's the law stating the time required to rapidly move to a target area is a function of the ratio between the distance to the target and the width of the target.
Right. The target is simply too small for the context.
Exactly. So the design system triad analyzes this data. The hypothesis is clear: we must expand the physical size of the visual radio button and dramatically increase the invisible interactive bounding box around it.
But in a rigid system, you don't just change a global token based on a localized hypothesis. If you make every radio button in the app 20% larger, you might break complex data-dense table layouts that rely on really tight vertical rhythm.
Precisely. You do not deploy globally on a hunch. You engage in rigorous research and development. You construct an A/B test.
The scientific method.
Yes. You deploy the old smaller radio button component to 50% of your user traffic and the newly engineered larger component to the other 50%. You isolate the variable and you measure the outcome.
And in this specific scenario outlined by the text, the empirical data from the A/B test is definitive. The cohort, using the larger design, sees a drastic drop in missed clicks. Form completion rates increase. Time on task decreases. The new organism is undeniably superior.
Now here is the critical operational step. What do you do with that victory? A mediocre team updates the React component, merges the pull request, and moves on. But a world-class design system utilizes what the chapter calls a bridging page.
Yes, the forensic documentation. This is so crucial.
When the new component is merged into the system wiki, the team authors a bridging page that permanently lives in the documentation. This page explicitly details the transition from the old version to the new version.
Right.
Crucially, it publishes the actual A/B test results, the click tracking ratios, and the heat map data right next to the component.
It is exactly like publishing a peer-reviewed scientific paper attached directly to your design files. You aren't just broadcasting a memo saying, hey, everyone, the radio buttons are bigger now, please use the new component. You're presenting the cold, hard forensic evidence of why the evolution occurred.
I really want to explore the cultural impact of that bridging page because it solves one of the most toxic cycles in product development.
The subjective arguments.
Yes. Imagine it is 18 months later. A brand new, highly opinionated senior designer joins the team. They look at a forum and say, you know what? These radio buttons look clunky. They take up too much vertical space. I prefer a tighter, more minimalist aesthetic. I'm going to submit a pull request to shrink them back down.
In a normal company that kicks off a 3-week political argument between design, product, and engineering based entirely on subjective aesthetic preference, it's completely exhausting.
But with a bridging page, that argument never even happens. The new designer opens the system wiki to find the component. They see the bridging page. They read the historical A/B test data showing that smaller buttons caused a 15% drop in form completion due to hit area misses.
The data instantly neutralizes the subjective argument.
Exactly. The designer realizes the current iteration is not an arbitrary aesthetic choice made by a predecessor. It is an empirically proven solution to a measurable user problem. The documentation truly functions as an absolute source of truth because it is backed by reality, not just opinion. It aligns the entire organization behind the scientific method.
That is the ultimate realization of a design system. It is a machine that absorbs chaos, processes it through rigorous rules, and outputs scalable, proven consistency. I mean, let's synthesize this massive architectural journey we have just taken you on. We started by examining the destructive chaos of unorganized scaling, the isolated mental forks, and localized decisions that turn a cohesive product into a disjointed Frankenstein application.
To combat that entropy, we explored the atomic design philosophy, the tree-like structure. We learned to stop designing pages and start designing indivisible atoms, combining them into highly specific functional molecules and organisms to completely eliminate microdecision fatigue.
We bound those atoms together with strict global rules, leveraging the immense power of design tokens. We translated those rules into a centralized JSON architecture, allowing a single semantic variable to mathematically dictate the rendering of layouts across entirely different software platforms.
We then explored the harsh reality of system governance, arguing that the system wiki must be gatekept in code, specifically a component-driven framework like React, to prevent documentation drift, while ensuring vanilla CSS snippets remain available to support stack diversity.
We humanize that rigid code through empathetic visual documentation, implementing the state, the obvious rule to destroy tribal knowledge and accelerate onboarding.
And finally, we established that a system must breathe and evolve through continuous research and development, utilizing A/B testing to generate forensic empirical data, which is then permanently documented on bridging pages to end subjective design arguments forever.
It is a profound framework for building digital infrastructure. And I want to reiterate, if you want to be the architect in the room, the person who understands how all these disparate disciplines interlock to create massive scale, you need to read the source material directly. We have been deep diving into Chapter 26 Design Systems from the book Design User Interface.
It provides the vocabulary and the structural blueprints that separate amateur product builds from true enterprise-grade engineering.
You can navigate to https.hype4academy.gumroad.com/Lou book. But again, please bypass the typing entirely. Just open your camera app, point it at the screen, and scan the QR code of the book link that we have placed right at the top of the description below. It is seamless. And before you close the description, hit follow on the show. We are going to continue bringing you these relentless, highly technical breakdowns to help you navigate and master the architecture of this industry.
We have covered an immense amount of theoretical and mechanical ground today, but I want to leave you with a conceptual challenge, a broader implication of everything we have discussed.
Lay it on us.
We've established that a mature design system actively restricts manual localized choices. It relies on atomic tokens, React-driven constraints, and empirical A/B testing to dictate the UI. The goal is to free up human bandwidth for high-level innovation. We are essentially applying the strict scientific method to user interface design.
The system curates the aesthetic based on data.
Precisely. But this raises an incredibly important question for you to ponder as you navigate your career over the next decade. As these design systems become increasingly perfect, as every single pixel of padding, every shadow blur radius, and every interaction state is governed by unbreakable algorithmic rules and continuous streams of user analytics, does the fundamental nature of the designer inherently change?
That's a deep question.
Do we transition from being creative artists who rely on intuition and visual flair to manifest a product into being behavioral scientists who simply curate and assemble data-proven components? And if the role of the designer at scale is fundamentally shifting from creation to scientific curation, how will you adapt your skill set to thrive in that highly mechanized future?